You hear the terms AUC and ROC curves thrown around all the time in data science, right? And they can sound, pretty complicated. But what if I told you they boil down to one single, really powerful idea? Today, we're going to pull back the curtain and see why it's all about the ranking.
So let's start with a little puzzle. Imagine you just designed a new exam for a bunch of students. You've got all their scores in a spreadsheet, but here's the catch. You haven't decided what the passing score is yet. So how can you tell if your test is any good? How do you know if it actually separates the students who get the material from those who don't?
And right here, this is the secret to the whole thing. The real measure of a good test, or any predictive model, isn't about some arbitrary cutoff you pick later on. No, it's simply about whether the scores did a good job of ranking the people who should pass above the people who shouldn't.
Okay, so let's tackle that first acronym, AUC. What is it, really? Let's get right to the core idea.
All right, forget about complicated graphs and jargon for just a second. The definition of AUC is actually beautiful in its simplicity. It's just the probability that if you randomly pluck one person who truly passed and one person who truly didn't, the passer will have the higher score. That's it. It's just a measure of how well-ordered your results are. And this simple idea gives us a really clear scale to work with. An AUC of 1.0, is absolute perfection. It means your test created a flawless ranking where every single true passer outscored every single true non-passer. And on the other end of the spectrum, an AUC of 0.5. That's no better than flipping a coin. It means the scores have zero power to separate the two groups. Okay, theory is great, but let's make this totally concrete. We're going to walk through a tiny little example, and I promise this is where you'll see just how intuitive this whole thing really is. So here are our exam scores. Let's pretend we have a crystal ball that tells us with perfect knowledge who really mastered the material. We've got 3 true passers and 6 true non-passers. Just kind of glancing at the scores, you can see the passers generally scored higher, but there's a little bit of overlap. So the real question is, how good is this ranking overall? Believe it or not, we can actually calculate the AUC for this little data set by hand. And the process is super simple. We're just going to create every possible pair of one true passer and one true non-passer. For each of those pairs, we'll check one thing. Is the passer's score higher? The final AUC is just the fraction of pairs where the passer, won. So first things first, how many pairs do we even need to check? Well, we have 3 passers and 6 non-passers. So you just do the math. 3 times 6 gives us a total of 18 unique pairs to compare. Now for the fun part, the actual comparisons. We go through them one by one. You take the passer who got a 92 and compare them to all 6 non-passers. That's 6 wins right there. You do this for all 18 pairs, and when you tally it all up, you find that in 17 out of the 18 matchups, the true passer had the higher score. There was only one single incorrect ranking. That passer with a 65 was outscored by the non-passer with a 78. And now, the final step. We just take our 17 wins, divide by the 18 total pairs, and we get our AUC score 0.94. And that, my friends, is an excellent result. It tells us our exam does a fantastic job of ranking the students correctly. And this is the most important takeaway of the entire explainer. Just think about what we just did. We have a single, powerful number that tells us exactly how good our test is. And we never, not once, had to talk about or decide on a specific passing score. We judged the ranking completely independent of any cutoff. Okay, so we've got this number, 0.94. Now let's finally connect it to that famous visualization it's named after, the ROC curve. So what even is this graph? The easiest way to think about the ROC curve is that it's a summary of what would happen at every single possible pass mark you could ever choose. It plots all the trade-offs for all of them, all at once. To understand the graph, we just need to know what's on the axes. So the vertical y-axis, that's the true positive rate. It's just asking a simple question. If we set a pass mark right here, out of all the people who should have passed, what percentage did we actually catch? And the horizontal x-axis is the false positive rate. This just asks the flip side of that question. Okay, at this same pass mark, out of all the people who should have failed, what percentage did we accidentally and incorrectly label as passers? And this is where it all connects so brilliantly. The ROC curve is just a plot of the true positive rate versus the false positive rate. And that AUC score we calculated by hand a minute ago, our 0.94, it is literally the total area under this very curve. And that, right there, is why it's called the area under the curve. All right, so we know what it is, we know how to calculate it, but let's finish up with the most important question of all. Why does this actually matter in the real world? What's the practical payoff of thinking this way?
Well, using AUC is incredibly powerful because it cleanly separates two different problems. First, you have the quality of your model's ranking, which is what AUC measures. And second, you have the completely separate business or policy decision of where to actually set the cutoff. AUC tells you how fundamentally separable your two groups are, and it gives you one single reliable number to summarize performance across every possible threshold you could pick. So the next time you see a predictive model, or a test score, or any system that's trying to separate one group from another, don't just ask about its accuracy at one specific point. Ask the deeper question, how good is its rank?